In our next section, we're going to look at BGP traffic engineering with AS path and MED, which again are going to be the opposite direction of what we previously saw with local preference and wait. So typically these attributes are going to be set outbound in order to influence our inbound path selection. Now, the one big thing to remember about the difference between these two attributes is that AS path is a transitive attribute, which means it will go out to all devices past your provider and beyond. So it's significant to the entire global internet, where multi-exit discriminator is a non-transitive attribute. So you set this out to your provider is not going to pass it on. Now, it's not to say that they cannot reset it if they want, but you would continue to have to reset it on an edge-by-edge basis. Now, as we talked about, there are going to be some more specific exceptions for MED that we'll come back to later. So here we're just going to look at the general path selection, and then later sections we'll look at the specific differences between how does deterministic MED work different than always compare MED, and so on. So let's take a look at our current topology, where again we have multiple ASs that are pre-configured for BGP peering. And we previously looked at how did we, from AS100, affect how traffic is leaving the network in order to get to AS54 or in order to get to AS254 by using local preference versus wait. But now we want to affect the path selection in the reverse direction. So let's say now from AS100's perspective, we want to affect how traffic is coming in. So first on router 6, let's go ahead and originate a new prefix. On router 6, we're going to go to, let's say, loopback, interface loopback 6. And we'll create an address, IP address 6666/32. And then we're going to advertise this into BGP. So under BGP 100, we'll simply say network 6666 with a mask of /32. Okay, next let's look at this route from router 2's perspective. So 2 has a number of peers that are inside its own AS, which is AS200. And if we show IPBGP for this new route, 6.6.6.6/32, we should see that we have multiple views for it. So right now, currently, we have the view that is from 5 through 4 and from 3 through 1. So notice here these values are different, which means that the next hops are not being reset as we're moving the routes from the eBGP neighbors to the iBGP neighbors. So if everything else is equal, it means that we would make the selection based on our IGP metric in order to get to those particular next hops. But we want to make the path selection higher, because from AS100's perspective, we don't want to have to rely on what is the internal routing structure of AS200 in order for them to route us their packets. So first, let's look at how is router 2 actually making this selection. If we were to do a trace to 6666, it goes to router 3, then 3 is sending it to 1, then 1 is sending it to 6. But let's say we don't want the traffic to go this direction. So right now we're going from 2 to 3 to 1 and then to 6. Let's say we want the packets to go to 5, then 5 should send them to 4, and 4 should send them on to 6. Now, depending on which particular attribute we're using, whether we're using MED or AS path, will determine where do we need to set the attribute, so on which particular peering, and are we trying to set it to a higher value or a lower value. Now, the simple one here is going to be AS path prepending. We would look at what are all the entry points into the network that we do not want to make preferred, and then we would do prepending out those. So whatever link you are prepending out, that means that the traffic should not be coming in there. Now, in this particular case, the traffic is going from 3 to 1, and if we don't want it to go that way, if we want it to go from 3 to 5 and then to 4, it means the prepending should be applied on router 1 out to 3. So next, let's go to router 1 and actually make this change. So first off, we're going to match on our local route. So we'll say IP AS path access list, permit $$. Now $$, and we need to give it a number. Let's say 1. Actually, let's say 100 for our AS. A caret dollar sign is a special regular expression that is used to indicate your own local routes. Because from router 1's perspective, when it learns the route from 6, since they are IBGP neighbors, there's no AS path information yet added. It doesn't actually get added until the route goes to the outbound rib, and we go to apply our outbound attributes to the eBGP neighbors. So here on router 1, if we were to say show IPBGP regex caret dollar sign, this means any of the local routes, which in this case, the only thing that we are locally originating in AS100 is that new prefix, 6666. But if we were to add other ones, for example, if we went to router 1 and said we had 1111/32, and then under BGP said network 1111, when we now show IPBGP with that same regex, which is caret dollar sign, this is going to mean both of those local routes because neither of these has an AS path. So next on router 1, out to the peering towards router 3, this is where we're going to add the additional ASs in the path length. So on router 1, we're going to create a route map that says out to router 3, permit. We're going to match the AS path list we created, which was path list 100, and we're going to set AS path prepend. Now, there's a couple of different options that we can do for this, and AS path tag we'll talk about later what that exactly means. One of the simplest ones would say the last AS. This is basically just a shortcut for not having to put the specific number in there. So it allows you to create this policy as a template, and then it doesn't really matter, are we AS 1, 2, 3, or 4, it's going to pick whatever the number is and then add that onto the path. So in our particular case, we'll say prepend AS 100, 100, 100, give it a couple times, and then this is going to modify the path. Now, technically, you can put any arbitrary value that you want in here, but in a practical case, it's bad etiquette to do that. So you should not be prepending someone else's AS unless specifically you're trying to black hole them from getting to you. Because if my AS is 100 and you advertise your routes to the internet with AS 100, I won't be able to reach you. But in general, you should not prepend somebody else's AS number. You're only supposed to be able to prepend your own AS. But again, technically, there's no restriction to do it. The CLI won't stop you from putting an error in there. Okay, then I need to add an additional sequence. We'll say permit 20, which is just going to allow everything else. Okay, next we go to the BGP process, and we say, as we're peering to the neighbor, so as we're going out to router 3, 155.1.13.3, use the route map to router 3 out. To router 3 out, outbound. Okay, if we then send them a new triggered update, so we're going to clear IPBGP outbound, and if we look on router 3 now and show IPBGP, we should see that those two paths, 1111 and 666, they're going to have long path lengths. Which, let me make sure I applied this correctly on 1. Let's look at the show route map. This is what the issue is. And what's kind of strange here, let's look at the show IPBGP summary. Show IPBGP neighbor 155.1.13.3 advertised routes. Technically, the parser should not allow you to do this. This is a parser bug. What I did was I called a route map that didn't actually exist. The desired behavior should be for this to explicitly permit, not implicitly deny. So this is similar to if you apply an access list at the interface and it doesn't exist, the router doesn't drop all traffic. It just permits all traffic and ignores it. But in this particular version, when I'm referencing a route map that's not there, it's the same as saying deny everything. And if you notice the difference here, if we show run pipe include router 3, I named the route map out to router 3, but then I applied it as the name to router 3 out. So be careful with that. You always want to check the policy once you actually apply it. This could have been a resume generating event right there. So let's say instead we want it to be out to router 3. Out. Then clear IPBGP star out. Let's see, on router 3, this should have affected the path, and we can see those are the prepended routes. So these routes should now be not preferred, and if we were to do the trace from router 2, we should ideally see that we're not actually going to use router 1 as the entry point. But we still are. Does anybody know why in this case it didn't actually work? Technically, the policy did work, but it didn't have the result of the traffic flow that I wanted. I wanted the traffic to go this direction, which is technically how I'm learning the route, but there's a key detail that we didn't really take into account here. From router 2's perspective, let's show IPBGP for 6666/32. Which is the best route that we're choosing? Okay, it's still coming from 5, right? But it says the next hop is 45.4. If we do a recursion to this and say show IPsef for 155.145.4, this says forward it out to router 3. When the route gets to, or the packets get to router 3, if we show IPBGP for 6666/32, okay, this is not the valid route anymore because we did all the prepending. The best route is the one that is via 155.145.4, and if we show IPsef for this next hop, the next hop goes to 1. Let's look at the routing table. If we show IP route 155.145.4, we're learning this as an IGP route between the different two ASs. Now, in most practical cases, you should not see this because autonomous systems normally should not be exchanging IGP. But in our case, they might, because we might have an unrelated IGP and BGP process, which is basically showing us here that BGP is not the one that really makes the decision. It's feeding the information to the RIB, but then the RIB actually has to do the route recursion. So from router 3's perspective, it does say that the path should exit through the route that 5 advertised to us. But the issue is that the next hop is this link here, which is being learned in that direction. Now, there's a couple different solutions for this particular problem. One of them would be to not exchange the IGPs. So if router 1 and router 3 were not IGP adjacent, router 3 shouldn't know the path in that direction. The other way would be to change the next hop. So if router 5 is the next hop as it reports it into the internal domain, it means that it should be the egress point for that particular packet. Now, if we were to look at between router 3 and router 5, how are they actually peering? If we show IPBGP summary, it says I'm peering with 155.105. If we show IPsef for this is a connected link. It's attached on the tunnel. This means that if router 5 were to take the eBGP route and report it into the iBGP domain with this next hop value, then router 3 would actually send the traffic that way because that's how the route is ultimately recursing. So the point of this being is that you do have to take into more into account than just the BGP attributes. Just because BGP says you should go that way doesn't mean you actually will. It depends on how IGP recurses to the next hop value. So again, the other solution would have been not to run IGP between them because 3 and 1, they don't really need to run EHRP. It's just with this initial config set, it's purposely set up that way to show that this is a potential issue that you need to watch out for. Okay, so the change I'm going to make without having to reroute everything, I'm simply going to go to router 5, and if we show run section BGP, I'll say when we advertise routes out to router 3, we're going to set the next hop to myself. Okay, if we then clear IPBGP star out, and we look at router 3 and look at that particular route, 26666/32, it says now the next hop is router 5, and now if we do the trace, we should see that now it goes the should go the correct direction. So it's going to 5, 5 is sending it to 4, then it gets to the destination. Now also notice that on router 5, it is directly peering with 2, but it's not setting the next hop itself to router 2. That might be another consideration as well, because we're learning the route from 5, but previously the IGB route was pointing to 3. This is where you could potentially get into a looping condition that if your IGB and BGB don't agree, they might both be pointing back and forth at each other. So the ultimate verification for this is not to look at the BGB table, it's to look at the traffic flow. If the traffic flow doesn't actually go the way that they ask you to make it work, then you wouldn't get credit for the points within the scope of the lab. Now, in a practical design, the worst case is that you actually do cause a loop in the traffic and you black hole it. So again here for the AS path prepending, you want to prepend out the connection that you do not want to use for the return. Okay, now let's look at this in the reverse direction. Let's say that router 2 originates a loopback 2222. So on router 2, we'll have loopback 2, IP address is 2222. And under BGP, we're advertising this with the network statement. Okay, if we then go to AS100, let's say from router 1's point of view, and on router 1 we say, how do we get to 2222? It says I have multiple paths. Currently I have 2 available paths, and the best path is number 2. I could either go to router 5 through 4, or I could go to router 3 through 3. Now, without even looking into all of the other attributes, I'm going to assume here that the choice is made simply based on the external versus the internal route. Because we're the same AS path length away from the AS, where we have multiple routes out to that same provider, so it means normally you would simply choose your external routes over your internal routes. So router 3 says route, or router 1 here says route out of the AS because this prefix does not belong to us. If we're learning it through IBGP and EBGP, it means it's not your route. Okay, but then let's think about how can we modify this. If we want to choose from AS200's perspective, how the traffic is returned, we first need to know what are the different border routers that are actually peering with the rest of the network. Okay, so let's say we look at from router 3's perspective, show IPBGP summary. We see we have a peering with router 1 in AS100. So there's a peering between 3 and 1. We knew about that one already. And let's look at router 5, show IPBGP summary. We have a peering between 5 and 4. Okay, so right now there's only 2 possible peerings, those 2. Now from router 2's perspective, if it wants to modify how the traffic is received back in, we are not going to be able to apply this policy directly on router 2. Now the reason why is that if we were to do AS path prepending, you cannot prepend out to an IBGP neighbor. You can only prepend out to an EBGP neighbor. But let's say we want to set the med value. Okay, router 2 right now has multiple peers, I believe. I think it's peering with 3 and 5, which it is. Okay, it's peering with 3 and 5. And so let's say we do this. Let's say that and let's actually look at 1, 4, and 6 and figure out how are they routing to get there. So we're going to router 3 from router 1. Router 4 is going to router 5. And then router 6 is probably going to go to 1 because 1's the reflector. Okay, so the traffic is coming in a couple different places. From 6 and 1 it goes that way. From 4 it goes that way. Let's say again that we want all the traffic to go from router 4 out. Okay, so we don't want to use this peering anymore. So on router 2's point of view, we're going to set the med. We're going to set the med as the route goes to router 3, and we're going to set the med as it goes to 5. When AS100 receives this in, we want to say that the med value is low on this side and high on the other, because we prefer a lower metric. Okay, just like IGB metric, med is the BGP metric, it's normally signaled from the IGP route. So when you do the network statement, it copies the IGP metric into the med in order to influence the other AS's view of your internal topology. Okay, so let's say on router 2 we're going to make this change. We're going to say that we're first going to match our route. So we'll have IP prefix list 2 permit 2222/32. We have a route map that goes to router 3 that says match IP address prefix list 2, set the metric, which is the med, and we're going to set this again to the higher value. So let's say we set it to 200. We're then going to permit everything else. We then have a second route map that's out to router 5. To router 5, we're going to do the opposite. So we're going to match the prefix list, and we're going to set it to a lower metric. So let's set the metric to 100. Then we're going to permit everything else. So if we show run section route map, two different ways the prefix can go. We're saying it should be preferred for the traffic to come in from 5. It should be less preferred for the traffic to come in from 3. Okay, now we actually apply the policies. If we show run section BGP, let's say that as we go to router 5, we want to apply the route map to router 5 outbound. Then as we go out to router 3, we have the route map to router 3 outbound. Okay, let's clear IPBGP star out. This is going to affect the new policy. And then let's see, did this actually affect the traffic on the way back in? Well, it affected something, but not really what I wanted. What happened was that we're hopping over a different segment internally to their network, but it did not affect AS100's egress path out to AS300. Okay, it's still going via router 1. So let's look at this from 5 and 3's perspective. If we now show IPBGP, regular expression $, so that's our local routes, we see that there is a difference in the metrics. Okay, the metric is 100 here and 200 there. We're preferring the one with the lower metric. We can see that's the best path. If we do the same thing on router 5, it should be similar. Okay, we have the path from router 2, and it has the metric of 100. That's the lower value. That's the one that's going to be preferred. Now notice here that router 5 doesn't know about both routes. And the reason why is that 3 cannot advertise its non-best path. Which is okay though, because we don't want to advertise that route. We don't want that one to be best. But again, the point being is that the different routers internally have different views of the BGP network based on where the best path selection is occurring. So in other words, 5 and 3 are making the correct decision, but the external AS is not. AS100 is not routing the correct way. So let's look at this from router 1's point of view. Why is 1 not choosing to go that way versus going this way? So on router 1, let's say show IPBGP for 2222. It says the best route is still from router 3. So what's wrong here then? Okay, one is external, one is internal. That's right. But what did we say about the path selection order? Does med come before external versus internal? It does. So we go wait, local preference, AS path, and then med. Okay, there's other ones in between, but those are the 4 that we're mainly caring about up to this point. So assuming that we're going in that order, right now the local preference is the same. The weight is not set because the weight's not listed there. The AS path is the same. But what's wrong here? The metric is 0. That's not what we signaled it as, right? We signaled the med as 100 and 200. But the issue is that the attribute is non-transitive. So the med value, even based on this simple example, it is difficult to figure out where you might need to set the med, because you need to make sure that it's on the path towards the eBGB router where the attribute will actually be maintained. So in other words, 2 setting the med out to 3 and 5 doesn't accomplish anything, because the med value gets stripped when 3 sends it to 1 or when 5 sends it to 4. Or in other words, the change cannot be made on router 2 in this case. We would need to make it on the border routers on 3 and 5, but basically do the exact same config. The difference is that we're going to set the med high as it goes out to router 1, and we're going to set it low as it goes out to router 4. So let's try this on router 3 now. So we're going to do basically the same exact policy, but we need to do it 1 hop further up in the network. Or actually, technically, in this case, it's downstream, further downstream from the destination. So on router 3, let's just say for everything, okay, to keep this simple, let's just say route map to router 1, set the metric to 100, actually 200. Okay, then router BGP 200, neighbor 155.1.13.3, route map to router 1, out. Okay, then router 5 is going to do a similar config. We'll say route map to router 4. That says set the metric to a lower value. So we use 200 on the other side. We're going to use 100 here. So that's 200. This one is going to be 100. And then under BGP router, BGP 200, the neighbor is 155.145.4. Route map is to router 4, out. Then let's apply the new attributes, clear IP BGP out, and we need to say this on 3 as well. So now on router 1, let's see, did the med actually get exchanged? Now it did. Now we're looking at a value of 100 versus 200. 100 is lower, so now that becomes the best path. Now we could still theoretically have an issue of forwarding though, because we ultimately have to forward towards the next hop. So we might want to actually hide the next hops, and when router 4 sends the route in, or when router 1 sends the route in, we may want to set the next hop to ourselves. But it ultimately depends on, inside of AS100, how do they route to reach this address over here? If they route this way, then that's not what we wanted. We wanted the packets to go that direction. So let's see from the rest of the AS, when we actually do the trace, let's see which way it goes. 2222. Okay, that's correct. It goes out to 5. From 1's point of view, it goes to 4 to 5. That's correct. And then 6 must implicitly means it goes this way, because if we were to transit through 1, 1 would intercept the traffic anyways. So again, then a couple other considerations here. The attribute itself doesn't necessarily mean the way that you're going to forward. You have to look at the association of the next hop and how IGP converges, or how IGP recurses towards it. How does it find the outgoing interface? Okay, the other thing is with med. Med is a non-transitive attribute, and by default, you only compare it when the route is coming from the same AS. So here in this case, router 1 is saying I have a route that came in from AS200, and I have another route that came in from AS200. It is going to be compared in this case. But if 3 set med out to 7 and 6 set med out to 7, then that's not going to work. Because router 7 says it's coming from AS100 and it's coming from 200. They don't know the details of their own internal, of each other's internal topologies, so the IGB metric doesn't even matter. Because remember what you're trying to signal to med. I'm trying to tell you guys what my internal domain looks like, because I'm copying the IGB metric to the BGB metric. Now we can enforce this if we want to, so we can say BGB always compare med, or in the case that there's lots of diverse connections between the providers, we could do deterministic med, We'll come back to that a little bit later. It changes the order of the path selection of med itself. When do we look at, or basically how do we order the prefixes when we go to compare one versus another? But in general, with these four attributes again, local preference and weight, we're going to set them inbound. They're going to affect our outbound traffic flows. AS path and med, we would set them outbound to affect our inbound flows.